Hello. So another LXD release, another stream to kind of go through the different features on this one, and well, let's get started. So I've got my usual VM here with leftovers from last time. So it's running MAS with a few virtual machines. Right now it's running on LXD 4.7. If we look at the snap config, it's running stable. So what we're gonna be doing here is do LXD and refresh from candidate, which should then pull LXD 4.8. Here we go. So maybe before I go to much more details, LXD 4.8, the majority of the changes have actually been bug fixes. We've fixed a lot of issues around storage and networking, but still managed to put quite a few nice new features in there. Okay, so that's been refreshed. And we can see we're now on 4.8. I'm just trying to change things a bit here. All right, so I'm not sure why I'm not seeing the chat for the stream, which is unusual. I'm not sure why it's not working. Anyway, so I might not actually be able to answer anything that's in the chat, unfortunately, because I'm not seeing it on my side. So we're on 4.8, and the first feature we can take a look at is being able to play with TPMs. So for that, we're going to be creating a new, let's just create a new VM for now. And might as well launch also a new container just for good measure. We'll use the same image, but as a container. Looks like we already had the right container image, so that's convenient. On the container side, all you have to do to play with that is do something like C1, then we do call of device TPM, the type is TPM, and we just run it on dev TPM 0. And now if we go in that container, you've got the TPM device. The same can also be done with the virtual machine. So we're going to be looking at that next, just waiting for the new image to unpack. Okay, and I do have the live chat back now, so that's good. I can answer any questions that might show up in there. This is taking a tiny bit of time unpacking that Ubuntu image. Maybe worth mentioning while that's going on. So this is completely based on the software TPM. We can actually see it if we look at the process list. We're gonna see down here, MAS is running, then we should have a bit later on our C1 container. And if we look under LXD here, we can see SWTPM running. So the way that looks like is it's gonna be creating some temporary TPM devices here, TPM 0, TPM RM0, and then that's passed into the container. For the virtual machine, it's slightly different. The way that works is it's still using SWTPM, but instead it provides some kind of socket that integrates with QEMU, and QEMU is then takes care of sending that into the VM as a TPM device. So let's see what's going on. Should see that VM starting shortly. SWTPM. Yeah, this is starting. Ah, there we go. Okay, let's wait for that one to boot. As usual with virtual machines, we can't easily do hot plug on a number of devices that includes the TPM. So that VM is currently starting up without any TPM attached. Then we can add the TPM and reboot. Well, can stop the VM, add the TPM, start it back up, and it's gonna have a TPM device. Okay, so it's doing its initial boot followed by its reboot. We can actually do the graphical console once it comes back online. Again, like virtual machines in this environment are a bit slow. That's because of the desktop that I'm using itself being virtual machine, and so everything is nested. That just makes that part a tiny bit slower. But we should see that virtual machine come back online shortly. Yeah, so QEMU is running. I see V1 is running here. So that should be responding now. Yep. And we have, let's see, it might already have booted actually. Switch terminal. No, not yet. Not seeing a login prompt on anything. Yeah, okay, boot screen. So that's a good sign. It might actually have finally given us a login prompt now. Anyway, let's cancel that and see if we can get the shell in there. Come on. Okay, so that virtual machine is properly working now. I'm not sure what's going on with my terminal. I somehow can't seem to do anything with it. It's weird. Anyway, maximize. There we go. Okay. So right now, if we go and look, we won't see any TPM devices. So we'll just stop that virtual machine. And then do the exact same thing we did with the container. So device add v1 tpm path dev tpm0 and start the VM backup. This time it's gonna boot up with a full virtual TPM, then we can play a bit with it to just make sure it works properly. And then we'll get onto our second point, which is also VM related. It's like improved file system transfers. All right. So it's starting back up now. So introducing the next thing after we're done with CPM. We've been doing some work to improve the performance of sharing file system with virtual machines. And the way we've been doing that so far has been by using 9p as the effectively virtual network file system used for a virtual machine accessing a shared drive exposed by the host. It works fine, and it's quite widely supported across many operating systems and different Linux kernels. The main issue we get with it is the performance is not very good. So we're now also doing VirtIOFS, which is the new fast alternative to 9p, and LXD effectively supports both and always uses both now. All right. I think it's TPM2 tools, that's the main package to play with that. Play with our new shiny TPM. Okay. While that's installing, we can just check again on the SWTPM front. So now we see we've got two different SWTPM instances running. There's one running in char dev mode, which is what's used by the container, and we've got a second one running in socket mode, which is what's used by QEMU and virtual machine. So with the tools installed now, we should be able to do, well, first of all, we can check that we do have the TPM devices in. We can see them here. And we can do a quick test. What can we do? get test result, I guess. All right. So that's pretty simple. I mean, there's currently no data actually stored in NTPM, no values we can really do anything with, but we can definitely just ping it and make sure that it does respond properly. I'm not sure if some of the other stuff works, like get, I thought get time worked on my laptop, just straight out of the box, but maybe not. Is there any other command in there that looks like it would be an easy thing to just play with, but doesn't look like most of them expect arguments. There's a self-test. Let's see what that does. Okay. Did it return 0? Yeah. Okay, so I guess the self-test succeeded. But yeah, now the VM has a TPM that could be used for a number of things. It can be used as a way of running an HSM, so you effectively like encrypt a key store with, you seal it with the TPM, and then TPM is used to unseal it. The other thing the TPM can do is effectively be used for storage of the disk encryption key, so that the VM disk would be encrypted and gets then decrypted on boot using that TPM key. The idea there being that if the disk somehow gets cloned or pulled somewhere else without the TPM state as well, then you can't unseal the disk and nobody can actually access it. And the last thing would be used, what TPM can be used is for measurement of like a whole variety of boot components and binaries and everything on the system. That log can then be sent out for remote attestation to detect if a system is behaving as expected or not. Okay, so that was the TPM side of things. Now I can quickly show what it that whole VataUFS thing I was mentioning, which is the second big feature in this release. So if we look right now on what's used on that VM, we should see something called a config drive that's mounted here on run LXD config/drive. It's, as we can see, this VM is using VataUFS. That just means the VM is recent enough that it supports it. And just to prove that we are still exporting everything as 9p as well, we can mount the exact same config drive using 9p. So now if we look at MNT and we look at what we had above, we see it's the exact same thing, just exported over 2 different protocols. The config drive itself is not very interesting because it's read-only, it's tiny, so there's really not much point in playing with it as far as the benefits of VataUFS. But what we can do is we can just shut down that VM. There we go. And we're gonna add a new disk, call it home. And we're gonna export a home directory into MNT home inside the VM. So do it like that. And then start the VM backup. So this time it's actually gonna be doing both full 9p and full VataUFS on that path. So we should actually see 2 different daemons start under LXD. Let's see if it should be there already. So actually, no, they're not there yet. They should show up shortly. Because like right now, if we look what we've got under LXD, we just see the SWTPM used by the container. The SWTPM used by the VM itself is not running yet. And we should then see 2 extra processes show up for the disk handling. Oh, there we go. It's happening. So now we can see SWTPM sockets. That's what we had already for the VM, for the TPM. And now we can see 2 different set of processes. VataUFSD, which is being configured to share. This one is for the config drive. Then we've got another VataUFSD here, which shares the home directory. And we've got a VTFS proxy helper that's for 9p that also shares the home directory. Now VM is starting. With a bit of luck, it's already booted and we can use it. Let's see. This is really significantly slower than when I just do it on my laptop. That VM in VM thing does make things quite a bit slower, but it's making the recording and sending that live stream much easier. Let's see. Okay, it is supposed to be running, so was probably just still booting at the time. And this one should actually connect this time. Come on. There we go. Okay, so now we're inside that VM. Let's see what we have. So we should have an mnt home that shows my home directory with everything inside it. We can see some recordings, some stuff in there. Now, if we look at proc mounts, there we go. We see it's mounted over UFS. Now let's create a new mount, call it 9p home, and we'll mount the exact same thing, but over 9p in that one. So first, let's start kind of the old way. So what we're going to be doing here is just take a bunch of zeros, dump them into a file, write them in chunks of 4 megs, and let's write 100 of them. And once they're written, make sure that everything is flushed to disk. So it's just writing 400 megs of nothing and making sure it's properly written and then returning. That's going to give us some performance metrics. This is not particularly fast right now. I think it's actually the slowest I've ever seen that. We could take a peek on the, okay, it finished. 15 megabytes per second. And we've got our 400 megs file. Okay, well, let's repeat that on the other mount, which is using UFS. Okay, so that's at least twice as fast. That's a lot less impressive than I usually noticed it. Again, that's because of the VM in VM thing and the way IOs are set up. On my laptop, that runs a pretty decent SSD instead. I get something in the neighborhood of, what was I getting? I've got that in the announcement. I was getting up to 80 megabytes per second on the 9p side, and I was getting around 500 megabytes per second on the UFS side. So quite an improvement. And we've seen even more impressive performance differences before. I don't know that I necessarily have enough files in there to make a test like this particularly meaningful, but we can try. So just listing everything. So it's doing listing every single entry on the entire home directory under 9p. Just taking quite a while. I was actually expecting it to be faster even on 9p. And then it will show us how long that took at the end. Alright, so it took 26 seconds. That's really not fast. Let's see if UFS does any better. Just to clear any potential issue there, because they're both separate mounts with separate file systems, the page cache and the Linux caching infrastructure is not gonna help the second test be any faster than the first, because they're really two different mounts. Okay, well, that was quite a difference. So yeah, UFS by its design also makes it significantly faster to easily handle a lot of different files and very quickly moving from one to another and sticking within a file as well. 9p in this case actually didn't do too bad at just bulk writes or bulk reads. But yeah, as we can see, there's definitely a bit of a difference. I guess the last test we could do is just reading back 400 megabytes file and just dump that into null and see how long that takes. Okay, so we just read 400 megabytes of nothing in 0.6 seconds on UFS. Then let's do the same thing on 9p. If it writes about as fast as it, if it reads about as fast as it did writes earlier, then we would probably expect that to be 30 or 40 seconds. Okay, it's quite a bit faster on reads, clearly. It managed to read 400 megabytes in 16 seconds, but that's like significantly slower than VertaUFS that just did it in 0.6. Okay, so that's really the main two features in this release. We do have a few more things. We've got cgroup v2 support, which I can't easily demonstrate because Ubuntu is still on cgroup v1. That being said, we do have daily tests we've now put in place that will test cgroup v1 with swap accounting and cgroup v2. So you can easily go and check that out on our Jenkins server. If we look at our cgroup test, here we go. Let's open the cgroup v1 swap accounting and cgroup v2 ones. So on the cgroup v1, that's a cgroup v1 test, that's a cgroup v2 test. And what we can see is it installs, creates a container, and then what it does is it validates the initial state of things. So it validates that without any limits, we're getting the same number of CPUs as the host, that the memory also matches, that the swap also matches, that we've got access to all the CPU shares, that the number of bits is unlimited, and the swappiness is where we expect it to be. And lastly, that network priorities are also aligned. Then what it does is it sets a bunch of CPU limits and validates every time that the output is correct. Does CPU priorities, does CPU shares, it does CPU time quotas as well. Then we validate some amount of memory around putting limits on memory, then validating the swap behavior as well, turning off swap entirely, seeing how that behaves. Validating that the limits themselves work as expected. So we turn on soft enforcement for memory. We write a bunch of stuff into a tempfs that will exceed the memory limit effectively. Make sure that this will not cause any problems. Then we do another test that this time will exceed the memory limit. And we make sure that the process does get interrupted and the kernel trigger the out of memory killer effectively. Then we clear all those memory limits, go on to process limits, making sure that if we set a limit, the limit is applied inside the instance. Then the same goes for networking, where this one we actually do a network transfer test. So we install iperf, then we test upload and download without any restrictions. So we see 12 gigabit and then 14 gigabit here. That's the more readable output here, so 12.7 and 14. Then we apply a limit of 15 megabit in upload and 200 megabit in download, and we run the test again and we check what we get, and we're getting 40 megabit and 182 megabit, so the limit is clearly applied, and that passes that test. Then we do disk priority if we can, which many systems don't support, so this one actually skipped the test. Then we test both IOPS and block byte limits. So we see the IOPS here being set. We validate that it made it into the right configs. Then we do the same thing on the byte limits, validate that this is fine. Then we test freezing the instance. So we do pause. We make sure that we can't interact with it because it's frozen. Then we start it back up. cgroup v2 is the same, but much more noisy because the snapd doesn't actually do cgroup v2 properly. So every time we try to run a command, it complains about it. But we can see we're doing the same thing, we're validating the initial values. Then we go on to set some limits around CPU and validating them. Then we've got the memory stuff here. Network priorities we skip because they don't exist in cgroup v2 yet, just like we also skip the swappiness tests on the memory side because same thing, they don't exist. Then we test the network throughput, that still works as expected. We test the disk limits, those also work as expected, and we validate the freezing at the end, which also works as expected. So cgroup v2 is effectively at parity with cgroup v1 in LXD, except for swappiness control is not implemented in cgroup v2, and network priorities are also not implemented in cgroup v2. That's the only two gaps, and they're kernel gaps that will as soon as something shows up in the kernel, we'll go and update that in LXD. Now, onto some ZFS kind of specific things we've added. Let me just get out of that VM, get a root shell here, and look. I don't think I've got the ZFS tools installed, so I need to install those. That will let us see the actual data sets that ZFS has set up on the system. And we can see the changes we made at that level, well, the extra options we've added more like. So kind of normally the way things work is LXD is image based, the image is downloaded, it's unpacked, it's put into a ZFS volume, well, ZFS dataset. A read-only snapshot is made, then that snapshot is used as the source for any instance we create by effectively cloning that snapshot into the new instance. That's the basics of all that stuff works. We can probably use ZFS already while it's finishing installing. So if we look at all the times and we just list the name of the volume and where it came from, there we go. So we can see what we have under LXD right now. One thing we can notice here is like all the virtual machines have no origin. That's because they were created as an empty VM for Maz to then configure. But we can see that the V1 that we're using, that virtual machine, we can see it is a clone taken from that particular image. So we've got the image fingerprint, and then we've got both the file system volume and the block volume and read-only snapshot. So they're clones of 0f, so they're clones of this thing. Then the containers, so C1, which is our new container, is a clone of 9e, which is this thing here. And the existing container that runs Maz is from an older image, which has since been deleted, but because it still recorded that origin and the origin must always exist, it's effectively stored here as a deleted image. So that's the way things normally work. There are a few knobs we can use, and we can show that. So one example here would be if I was to make a copy of C1 as C2, gonna be seeing that C1 now got a new automatically generated snapshot, and C2 was created from that particular snapshot. The impact of that being that now if I was to delete C1, I think it's running, so just kill it. Okay, so now if I look at that, we still have C2 because obviously we wouldn't want to lose that. It is still, its origin is still that temporary snapshot. But now we can see it points, the snapshot has been renamed to deleted containers, then a random UUID, and then the random snapshot. So this thing here is still the container. Well, oops, hold on. Yeah, this thing here is the container that we deleted. C1 effectively still exists because C2 references it. Now, if C2 was to go away, then they both go away. Which also means that the image they were created from, this one here, is no longer being referenced. So if that image was now to be deleted, it would be completely gone from ZFS. Okay, so let's just recreate that. So we'll just do 1, 2, 24 cloud, so we'll recreate C1. Okay. And now we can look at some of the options that are available around that. So now C1 has been recreated, is again a children of the image. There is a config option that can be set on the default pool called ZFS clone copy. And if we set that to false, and now we were to launch a second container, that's gonna take significantly longer, as we can see. Because it's not gonna be using clone, it's gonna effectively duplicate the storage entry entirely, which means it's no longer tied to its original image. Okay, so it got created, it's starting up now. Okay, So if we look, we'll see that they both use the same image, but C2 shows nothing as its origin, while C1 shows the image. Similarly, if we were to now copy C1 into C3, this is also going to be using a full copy, not using a reference. So we can see that C3 does not have an origin set either. That's already been around for LXD in a long time. The feature we've added now is called Rebase. So if we set Rebase and we do another copy of C1 to C4, we'll see a different behavior. There we go. So now we can see C4, but we can see that its origin is the exact same as C1. That means that when C1 goes away now, it fully goes away. It doesn't get renamed to like a deleted container. It's completely gone. C4, but C4 doesn't, unlike C3 in this case, does not duplicate all of the data of of the image. It only duplicates the delta that C1 had with the image. So that can help quite a bit by only ever retaining the images that the containers were initially created from, but not retaining all of the source containers in a chain. Because obviously you can imagine that if you create C1 and you copy it to C2, then you copy C2 to C3, then C3 to C4, then C4 to C5, and you delete everything except C5. Now you're retaining the image C1, C2, C3, C4, just so that C5 can exist. That can really add up. This method would mean that C5 would only be linked to the original image and the rest would go away as soon as they get deleted. So that was for the new ZFS Rebase option. The other thing we've added is the ability, well, it's a tiny change in the command line really, but it's to let you reuse a snapshot name. So if we list, it's running on the system. The system is surprisingly slow. I'm not sure exactly what's going on. Okay. So if we were to make a snapshot of, say, C2, so make a snapshot called foo, and now we want to create a snapshot, the same snapshot again. We're being told it already exists. You can do that. Well, now we've got a reuse option that will just delete the existing snapshot, create a new one, and not have us require the client, the user, to figure out that the snapshot already exists and go and delete it and create it again. So it's a tiny improvement, but it's quite welcome. And the last really visible thing we can cover is lifecycle events. So you can do something like this in LXD, which will, those are the logging events. Actually, we actually want lifecycle. There we go. So lifecycle events are gonna be start, stop type things. If we were to start C3, and we see here, container started C3. And if we were to stop C3, we get shut down because it was a clean shutdown. If we start again, started, and if we do stop and we kill it, that should show stopped, container stopped, I believe. There we go, container stopped. We already had that, that's fine. The new thing is now if we do a restart, specifically I think a force restart. This is not working. That's interesting. Why aren't we getting a new shiny restart event? Let me try it that way. So it looks like there's a bit of a bug here. That's supposed to work better than what we're seeing here. There we go. So this one did work. So it does get container restarted as a new event that will replace the previous stopped and started, which didn't give us that context. Clearly there's still a bit of a bug there that we need to fix so that outside restarts are properly treated as a restart and not as a stop and start, but it looks like at least container initiated restarts work properly. The last thing we have, and we can't really see it super well, but we can actually show a tiny bit of it, is if we look at logging events, so what would normally make it into a log file, and we do a basic query, like say we just want to query the state of C3, so this. we've always stored some amount of context. So we store the queries here. We see that what method and protocol and the endpoint. But now we also always store the username. The protocol was stored but not always logged. So now we always log the protocol, which can be either Unix or it is TLS if it's over the network, with then username being the fingerprint. Or it can be candid, which is also for TLS authentication, but when we use external authentication, in which case the username will be a valid username as well, like the username that you've used with your external authentication system. So yeah, in this case, we see it actually figures out who talked over the Unix socket and shows us that username. So in this case, root. If I was to do the exact same thing as my own user, then we should see here it's showing that user as well. And that's it for the new features in 4.8. As I said, the rest is like we've got a very long list of commits in the announcement. The vast majority of our other fixes have been around storage. Oh, it's actually interesting here. In this case, we're seeing, what are we seeing here? I think we're seeing MAS. Yeah, it is MAS. So we actually, it's funny on the task point. So we just got MAS connecting to LXD and doing a few requests. And in this case, we do see that it's hitting /1.0. It's also checking the status of some specific VMs like VM04, VM02. And as I said, it does show the protocol as being TLS, and it shows the username as being the fingerprint of the certificate. So that's what it looks like when you're getting a TLS connection. Alright, let's just close that. I'm not sure what's going on with this one, but whatever. And yeah, that's it for 4.8. So it's currently available in the LXD candidate snap for testing over the weekend. And we expect to roll it out to users starting on Monday, unless we get issues reported over the weekend that we need to sort out. It's also starting to hit other distros, and we've got the Windows and Mac OS clients also updated and available. That's it for 4.8. If you want more details, we've got the usual forum announcements that's linked in this video, and you can go to get anything else or ask questions there. And I'll see you folks in next video. Bye.